Okay, so let's go. We are here today for the PhD defense of Romain Brisse in front of the committee, which is composed for the reviewers of Professor Günther Pernuhl from Universität Regensburg in Germany, as the associate professor Maciej Korzinski of CMAC. For the reviewers, for the examiners, we have Professor Vincent Nicomet from INSA Toulouse, Laetitia Deschnam from Luxi, and the supervisors are Professor Jean-François Lalande from Central Supélec, Frédéric Majorzik from DGA, and last, I will be head of the committee, and I am Alexandre Garnier from Université de Rennes. Well, the floor is yours.
Thanks. Thank you all for coming. I will be presenting to you my PhD work today. It was done jointly with the Pirate team, formerly known as CERBERE, from Central Supélec, as well as the company Malizen, and the DGA. And my PhD is titled Exploration Recommendations for the Investigation of Security Incidents. And I believe it's complicated as a title, so it needs some context. When you think cybersecurity, you think attacks and attackers, and you'd be right to do so. But cybersecurity can be approached from a various axes and a number of ways. See, for example, you could try to prevent attacks even before they happen. That would be prevention, okay? For prevention, you have, for example, pen test, which consists of reuniting attackers that will, before real attackers can attack your company, try to attack it, find vulnerabilities, and patch them before they can be exploited. You have other axes like supervision, which is the actual detection of attacks, digital investigations while they are happening. There's remediation. Once an attack has happened, you have various ways of understanding them, such as, for example, reverse engineering, which consists in taking the binary code used by an attacker for his virus or ransomware or anything, and try to reverse it back to the source code that was written in order to understand it better, understand where the attacker is coming from, what it did, etc. And there's also incident response, which is involved because that's what we are going to be focusing on today. And of course, there's one last thing, it's testing, training, and educating people. In cybersecurity, this is essential because expertise is, and we believe human expertise, is the cornerstone of cybersecurity. For example, we conduct often red and blue team exercise. A red team is a team of attackers that will try to break some infrastructure, find vulnerabilities, attack them, exploit them, steal data. And while the blue team is a team of defenders that will try to either stop attacks or understand them afterwards. Okay? So, I was talking about focusing on incident response, okay? So there's a big workflow for incident response here, but let's just take an example, okay? Say you have an attacker. He has a virus, he wants to put it in your company, and, well, he is going to try and begin attacks on your company, and that will likely and hopefully trigger an alert, and the first part of the workflow is reporting this alert, starting an incident, and triaging it, which basically just means giving it to the right person to investigate. Then, let's say our attacker manages to put the virus on a server on your company, and he tries to, I don't know, steal passwords or something. This will leave a mark, traces. And this is where you can have a team of investigators that can try to resolve the incident with various steps like the data analysis, searching for a solution, applying it, eradicating and recovering any data that has been lost or stolen. And this is highlighted in green because it's, again, what we are going to be focusing on. But there's a final steps that is kind of out of scope today. It's closing an incident, Imagine your investigators are very good and they have managed to block and stop the attack, contain the menace, and so they will report on doing so that you don't fall into the same trap again. But we are focusing, as I said, on incident resolving. And to resolve an incident, the first step is analyzing data. But which data? Well, when you think investigations, you think logs often. A log is simply a recording of an event that happened on a machine, anything. That can be your personal computer in the company, a server, an intrusion detection system, anything that can record information. Okay? And they are specific and they contain lots of information. You have an example there. And this is just one line of log. For large companies, you can record tens of millions of lines like those every day. Okay? Which makes it very complicated to explore for this reason, quantity, and for other reasons. Like here, we can see problems with this log just by looking at it. For example, here you have fields which identify which information is in the log. For example, here you have a message field, but here you have another message field, which makes it really complicated to uniquely identify information in a log. And this second message field unbalances completely the structure of the log because it contains other fields, which is weird. Some of these fields even have value, even don't have values, like question marks. So logs have problems. Quantity, heterogeneity, multidimensionality, even completeness. So that's why we need analysts to investigate them during incidents. But investigations, what are those, actually? Well, it's basically just a process of exploring the logs I've just described to search for any abnormal behavior, and if you find any, to find steps to resolve it. That's as simple as that. But what's great today is that we can watch an investigation in action. So here we go. Look at the left part of the screen. You can see fields that are defining here. And that's all the fields that I've showed you in the log line we had 2 slides before. And you can select those you want to explore. Here we are in a case scenario where an analyst has been told that he should explore source IPs first. So he creates a card by drag and dropping the field and sees the visualization. He's searching for a specific IP that was given to him and doesn't find it. So he can just, for example, search it by himself. Simple as that. And when he does that, it will create a filter. And this is the filter you see up there. And it will do multiple things. First, it will, on the top left corner, you can see it will just show the events that are connected to this IP. So anything someone using this IP has done and that has been recorded, okay? And now we want to find information related to this IP because we suspect it is the IP of the attacker, okay? So we will drag and drop another field to try and find some new information. And sure enough, shocker, we find immediately a ransomware. There's here a trace of a ransomware being put on the machine somewhere. And that's great. We found some information, and we want to save it for later use. You can put a comment and to describe it. And the next part of this video is for later in the presentation. So you've seen what an investigation looks like, okay? So with this background, we were able to gather some problematics we want to approach in the thesis, okay? So there are those which I've talked about, and the final question is how do we actually help analysts? And we've added for ourselves some constraints for, just some constraints, because it's important to do so. And we want to not try to replace analysts, which means we want to keep them at the center. We want to keep their expertise for the work. We want to not force them to become experts in other areas, for example, visualization, as I've shown. And finally, we want to hinder their investigations, which, as you've seen, are already very complex, as little as possible, which is going to be an ordeal. Okay, so knowing that, we can dive into literature. So many things have been done in order to help analysts during investigations. There are automated solutions like intrusion detection system using playbooks for attacks that are detected but well known, so you can resolve them automatically. There are visualization systems that are pretty pro-efficient right now to explore more easily and more efficiently volumes of logs that are enormous. There is data pre-processing and enrichment. Logs, raw logs are very complicated to explore, so many people have tried to correlate alerts in order to group them, to make them easier to explore, once again. And there's also decision helper tools, once again in bold, because that's what we are going to focus on. But each of those solutions presents different problems, okay? So for automating solution, there's the loss of the human expertise, which we wish to keep at all costs. There's the additional expertise for analysts that I've discussed before. We want them to be able to focus solely on their cybersecurity expertise. And finally, there's, if you pre-process and modify data beforehand, before investigating it, you lose explainability and transparency, which are things we are going to try to address and go around in our work. So we are going to approach the problem using recommender systems. Recommender systems are basically really simple. It's just a piece of software that helps a user make a decision. That's as simple as that. All recommender systems are built in the same way, more or less. These 4 bricks. There's input data, because if you want to make a recommendation to someone, you need data to do it. Then you model this data to your needs to be able to use it for recommendations. Then there is a recommendation engine, which job is to select candidates into the data that may or may not solve the task at hand, and score them to find out which of these candidates for recommendations are the most likely to solve your problem. And then these candidates can be recommended to the user. Okay? So this schema you are going to see multiple times in the presentation, just to show you that every recommender system is built like this. So recommender systems also have different types. I'm going to use examples to show them to you in order for them to be really easy to understand, because there are lots of ugly words there. So a collaborative filtering recommender system is like what they do at Netflix. You watch a movie, you liked it, you give it a thumbs up, okay? Then Netflix and its recommender system does this. He takes the film you've given a thumbs up to and will compare it to other users that have given it also a thumbs up. And these other users might have liked other movies. And if they have, and you have this movie in common that you've both liked, they can recommend it to you, other movie you have not seen, and other users with the same taste as you have liked. That's the first one. The second one, the content-based, works more like the Amazon way of doing things. So let's say you buy a book, fantasy genre, for example, and you liked it, you give it 5 stars, and well, Amazon will do the same thing. It will just find other books that many users have given 5 stars to, also in the fantasy genre. It uses this time properties of items rather than as well as the ratings, but instead of basing itself on the taste of users, it uses the properties of items. That's the main difference between these two. Then there's knowledge-based recommender system, which are a little bit different. This time, they use actual knowledge, expert knowledge from the domain in which you are trying to solve a task. And when a user asks a question, asks for a recommendation, you will try to select actual knowledge in the base to give it to him. It's like kind of Wikipedia. And of course, these types of recommender systems have been used in cybersecurity before. They have been used to solve a number of different tasks, which I've highlighted some of them for later. And I just want you to note something, is that during an investigation, we cannot reasonably ask an analyst to give 5 stars to an alert. It would be too time consuming and just a boring to do so, and it would hinder them too much during investigations. So we don't. We have to, we have to choose from other input data to build recommender systems. So these are all tasks that can be solved using recommender system, but let me just rearrange them with something you've seen before, okay? We are focusing on this part, the green part. So what has been approached before is attack mitigation and facilitating investigations using recommender system. And we are going to present to you one work we believe is close to what we're trying to do, and that's NAVSEC. So this is NAVSEC. I told you you'd see this again. NAVSEC is also built like this. NAVSEC is a recommender system for 3D network security visualizations. Okay, so it uses as input data visualization interactions a user has with a visualization platform in 3D. Then it makes, once interesting discoveries are made along investigations, sets of visual interactions are saved. And these are using a nearest neighbor approach, used to make recommendations to users during new investigations. But that's a little bit obscure to comprehend, so let's just see it like this. So imagine you're doing an investigation and you're using this recommender system. You are interacting with the platform, and at some point in your investigations, you will find yourself close dimensionally to sets of visual interactions from past investigations that were deemed interesting, and so we can recommend them to you. And that sounds a lot like helping investigations without hindering users, and it's kind of like it, yes. It's user-focused, it's very accessible, it's even novice users can do so and even be helped by it. It's unobtrusive, so it's really integrated into the flow of your investigation, but it does have some problems. Like, you need a visualization expertise to use it properly. You've seen a 3D image, very complicated to interact with. There's mimicking. It uses sets of visualization interactions to make recommendations. It does not actually understand the cybersecurity situation at hand, which we believe is a problem. And then there's a problem that is specific to recommender system, and that's the cold start. The cold start basically is this. Imagine you have a recommender system, you want to do this, but you have only 1 or 2 triangles, not all of those. When you do an investigation, you might have this one and this one. When you do an investigation, the distance between your situation and a potentially interesting situation will be very far, meaning that if we recommend you to go in that situation, it might be inaccurate, even lead you on to false leads, and that will be bad. That's not having enough data to make good recommendations. That's the cold start problem in recommender systems, which, you get it, in cybersecurity is unacceptable. And there's one last thing. This is academic work, so what about evaluation? Does this work? Well, I just want to talk a little bit about this, because NAVSEC is a very interesting recommender system. But the evaluation is just one use case of one attack, a stealthy port scan, that is found out over 5 different sessions. We don't know if it's 5 different participants or not, and it seems to be converging to less and less interaction with the platform and seems to be working, but we have no actual way of being sure of it. So we've decided to work on evaluation a lot as well in this work, and there will be a whole section dedicated to it later. So yeah, from all of this, all the literature, we finally have some research questions we can get to. We want to, one, use expert knowledge, because we want to match cybersecurity situations with actual cybersecurity knowledge. We want to understand users better. We want to try maybe to understand intentions of analysts during investigations. And we want to be able to evaluate our work as well as possible, so we need data to do so. So we will be also working on how to obtain logs of our own. Okay, now we are going to talk about our recommender systems. You remember this again? And I'm putting it back again here, just to show you that it's the same thing as the next schema, just a little bit more complicated. So we've built, during this PhD, two recommender systems. There's one up and one down. The first one, KRAKEN, answered the first research questions, and the second one, MIMIR, answers the second one. Unfortunately, for this presentation, I will only be able to talk about the second one, MIMIR, but if you want just a few information about the first one, it is a knowledge-based recommender system. So remember, it uses expert knowledge to make recommendations. Here, it uses the MITRE database to gain knowledge and model it in a two knowledge base using the elastic common schema. And it uses similarity measures and a multi-attribute decision-making in the recommendation engine to recommend fields to explore to analysts. And even though I can't present it, I can show you a little bit how it works. Do you remember this? You see the video, and we've just saved a value because we found a ransomware, and now we want to know more information about this. So this is where KRAKEN comes into play, and he will make a recommendation here. Because he will try to understand the cybersecurity situation at hand and make interesting field recommendations in agreement with this situation. We quickly find that interface name might be interesting. So we create the card, and we find out that only one interface is used to deploy this ransomware. So we can now identify the machine on which it was deployed first. And in the idea of keeping explainability and transparency at a maximum, we also can ask for information on why this recommendation was made to us. Yeah, so that was a little bit about KRAKEN, and now we are going to talk about MIMIR more in detail. MIMIR uses a very different kind of inputs to make recommendations. It uses investigation traces. That means all the interactions a user has made with the data, the cybersecurity data, to explore it during an investigation. Then, from those traces, we are going to infer two things. First, their intentions, and two, investigation patterns. So, recurring groups of actions the investigators do in order to complete their investigations. We are going to model this into a Markov chain, which is just a probabilistic model that will allow us to select the most likely option. And then we will recommend it this time not in the form of fields to explore, but in the form of actions to execute in the platform. So let's get to it. We needed first investigation traces. So we built an experiment. We had 5 participants, 2 data sets, one of networks logs and one of system logs in order to keep diversity at a maximum. And each participant did 1 investigation on each data set, which yields 10 investigations of various time. And we now have investigation traces. But remember, we need to model those to be able to use them to make recommendations. So how from there do we get user intention? How do we translate these intentions into concrete actions we can do during an investigation? Well, let's say you're an analyst, you're investigating, you are making user actions. We can try to infer your intention, even if we manage to do so, how do we predict the next one? Well, during the experiments, we asked all our participants to say what they were thinking out loud. All their thinking process during the investigations was just explained in excruciating detail to us. And we asked questions about what their goals were, what they were aiming to do, how they were aiming to do it. And from this, we extracted 7 possible intentions during an investigation in the Maven platform. So these 7 intentions are the following. You have startup and discovery, when you are trying to find an entry point into a data set to begin your investigation. There is broadening and deepening, which means broadening, expanding the data pool you are trying to explore, getting a bigger picture. Then deepening, which is the opposite. You are trying to focus on something particular, maybe a value or a range of values. Then there is reporting your findings, which is what we saw in the video, just saving something for later use, anything, maybe a report. Then there is backtracking. Backtracking is hitting a dead end and trying to go back to a interesting previous state. And it's important because there's a nuance with searching for a new lead, which translates as I'm lost, where you don't have an interesting state to go back to. It's trying to go to another interesting point in the dataset that I have not planned. And then, since MIMIR was integrated to the platform after KRAKEN, there were already recommendations in the platform, so since it were not the intentions of a user, guided by recommendation is a category in itself. So, we now have intentions. We also need patterns, as I've said before. We've formally defined them here. A pattern is a group of two actions and their context. The context is important very much because let's see that in an example. You see here there are two patterns, and both patterns have the same action as the first action, but one has disable and the other one has include as context associated to the action. Include is what you've seen in the video. It's focusing on one particular value. You've seen it reduces the number of events you are exploring drastically, while disable is removing that filter, which means you're expanding the quantity of data you are exploring. And that changes completely the meaning of this first action. And which is why, when you complete the pattern with drag and dropping a new card here and disabling another filter here, you get intentions like broadening for the first one because you are expanding your data pool, and deepening for the second one because you are focusing on another value than the one you were focusing before. And now we have patterns and intentions. During our experiments, people were describing what they were doing, so we matched those together. We had a first set of patterns and intentions from the investigation traces, and then what we did is we wanted to cross-validate this and see if it's actually working and if other investigators will have the same way of resolving intentions. So we took two experts that know very well the platform, and we gave them the 7 intentions, and we just asked them to, in as many ways as possible, resolve each intention with patterns of 2 actions. And then we matched those. So the Venn diagram is not a scale, but it's actually quite a big part of it, the intersection. And it results in 39 resulting patterns matched with intentions. And that's, if you remember the schema, our model data of user actions and user intention that we can use to make recommendations. What we want, remember, is to predict the next intention a user might have. So what we did is that we modeled this into a Markov chain. That's a probabilistic model. It's easier to represent it using a matrix, but it works a little like this. Each possible state of the matrix is one of the 7 intentions, and a transition is identified by the probability of going from one intention to another one of the 7 itself or the 6 others. So when we want to make a recommendation, then what we can do is take the intention, here is X, so backtracking, and find out which next intention has the highest probability. Here it's B, 59%, and we can recommend actions that are linked to the broadening intention for people to do during their investigation. So that's exactly what we did, and a flow of recommendation looks a little like this in investigation. Now, you have still your analyst that's doing his investigations, that's making user actions. But if we detect him having made a pattern in his investigation, we infer the intention associated to it, and then we go through the Markov chain to find the most probable next intention, and we recommend actions linked to that next intention. So basically, we are trying to understand what an analyst is trying to do next in his investigation. And we offer him ways to realize that. So, There's still one thing I have to talk about. There's this again. You see, we've built a recommender system. It's all great, but we don't know if it works. We have to evaluate those because otherwise it's not worthless. But yeah, we want to know if this works. So we will add a new layer to our schema. You have evaluation now. Evaluation can present itself in three different possible ways. There are more quantitative results, so numbers and stuff, which are online evaluations. That's an actual use of a tool by actual participants. There is offline evaluation. That's more like maybe, machine learning papers that's measuring accuracy, maybe F1 scores, things like that. That's statistical work about the recommender system. And finally, there's more qualitative results. That's user studies. That's getting feedback from the user. Did they like it, basically? And I've added one last thing. It's data, because it's going to be a big problem and something very important to have. Good data to evaluate your work is essential. So we set out to evaluate MIMIR. Once again, I don't have time to present the evaluation of KRAKEN, but that's life. Evaluation of MIMIR. So first, as I've said, we need data. We've used the VAST 2012 and TC3 datasets to get the first 10 investigations that allowed us to build the recommender system. The Markov chain I've presented to you before is built on data that was investigated from these datasets. And then we found two other datasets that both have a comparable number of events within them, but they both are network and system logs, and they have significantly more investigations conducted on them, which is great for evaluation. And we use them to first perform an offline evaluation. So what's that? We were trying to see if in our model, in our Markov chain, we've had actually captured the behavior of an analyst during an investigation. So what we are trying to do is to see if traces of investigations are likely to be generative of a matrix. So let's take this table in columns. Let's take the first column. You see the VAST 2012 and TC3 traces have a likelihood of being generative of the matrix for the same datasets of 21.556. So that's our base number. And then what we did is that we compared this number with the same one for other matrices that are seemingly unrelated. So these traces have these 20 and 19 scores of being generative of these matrices. And then when we take random matrices, it's an average of 100 random matrices we generated, we have a value that is half the score. Which is great, because we show that the likelihood of us having captured behavior in our matrices is much higher than at random. And this result repeats itself for both other columns. And it shows that we might have actually managed to capture user behavior. But you're not convinced this recommender system works right now, right? I'm not either. So what we needed to do is to evaluate it again in another way. And what we did is we wanted to do an online evaluation. But to do so, we needed participants, data, anything, a new experiment, and that's what we did. This is the third contribution of my thesis that was done jointly with other members of the teams. And what we did is that we built an exercise called CERBERE, a red and blue team, if you remember the first slide. And we have instances of a scenario of attack that's playable. This means we created virtual machines that have vulnerabilities, and we had 13 red teamers attack them to find the vulnerabilities, exploit them, get access, steal data, anything. And we monitored them while they were doing so. And we gathered, in doing so, attack logs. So for my colleagues, they could label these attack traces and generate a data set. to work on, but our interest here is to get those data codes, ingest them into the platform you've seen in the video, which includes now MIMIR, and investigate those. We've had 9 blue teamers investigate those traces, and that yielded us new investigation traces we could work on. And this is where we get our online evaluation. Actual users actually using our recommender system and seeing if it works. But first, some statistics about this this exercise so you can realize a little bit about the volumetry of it. There were 60 VMs, which is quite a scale for a first iteration, which yielded almost a gig of attack logs and a repartition of networks, system and network loss for 2 to 1, 9 investigation and almost 20 hours of investigation. And for MIMIR, that meant 2,706 user action recorded, 729 MIMIR recommendations, and 83% of those were followed by users, which is seemingly a great result. But let's see it in a little more detail. You have here possible recommendations that can be made. If you remember the transition matrix, we recommend only the next most probable intention, so that for each of the 7 intentions possible, we have only 1 choice of recommendation, which means 7 possible choices of recommendation. 5 of those are represented in this experiment. Then we wanted to see if the recommendation was followed directly or with a latency. So we show 3 different bars of following the recommendation in the next action or next 2 or next 3 actions. And I want to go into a little more detail with you on 2 of those. The first one is RR, so report finding intention detected, and then report finding the intention recommended again. And what you see is that no one follows the recommendation directly. That's because when you have finished an investigation and have found everything, you start reporting, then you go back to analysis and do one or 2 maybe actions to get in another state, to save another state of the platform that is interesting to you, that completes what you've already reported, and that's why you have a much higher result in the next 3 actions for following the recommendation. And the second thing I want to show is the LL, the last one. It's searching for a new lead. This one we actually understood by getting the feedback of users after the experiment. What we saw is that the recommender system would say, oh, maybe you're lost, let us help you and find another way to start again your investigation, and would recommend some actions. And our participants said that, what does it cost me to just follow it and see if it's interesting? And so they just followed it every time. And if it was interesting, they would go on with the investigation. And if it was not, they would just repeat the process until they found an interesting point to go back to in the investigation. And yeah, that's pretty encouraging results for MIMIR, which of course need a lot of work. But I want to conclude on this evaluation part on saying that there are multiple ways to evaluate recommender systems. And we think that as much as possible, you should try to evaluate them in as many different ways as possible. Because as you've seen, each different way of evaluating a recommender system I'm losing my thoughts. Each different way of evaluating a recommender system yields very different results and very different information about said recommender system. For KRAKEN, I did not have time to present it, but the user study was actually the most interesting part of the recommendations because we've learned so much that helped us build the second one, which was great. So we've tried to do so. It's complicated, we know, to do as much evaluation as we could. We even tried to have as many data as possible. Even one of those datasets was our own, and we wanted also diverse profiles of participants. All the investigation you've seen at the dataset I presented come from different events, notably Capture the Flag event that reunites experts, students, postgraduates, aficionados, anything. So we are pretty glad that we were able to capture interesting behavior from those. And now we are getting to the end. So some conclusion about the thesis. We've made 3 contributions, 2 recommended systems that answer our first 2 research questions, a new way to generate data with the CERBERE exercise, and if I have just a few final words, the ability of recommended systems to get insight from data and also leave experts in charge and use their expertise to the maximum of their ability is, we believe, invaluable. And we believe that using a recommended system for cybersecurity has a great future, and I was so glad to work on this. And of course, we also have some perspective for future works after this thesis. So first, we want to make small improvements to MIMIR, notably work on should we recommend only the most frequent next intention there is, or could we recommend a combination of those, include some context to change the probabilities? That are questions we are asking ourselves at this time. We want to better industrialize the 2 recommended systems because they are integrated to a real platform, a real company, and we want them to be usable in this context. And then a little later, we would like to expand the input data of recommended systems. Notably, KRAKEN could use CTI, which is cyber threat intelligence, so data that are reports of attacks. And that could help us refine our recommendations, we believe, a lot. There is also this, working on recommendation triggers. We have not discussed it a lot in this presentation because it would take another 20 minutes, but it's very important. The frequency at which you can make and should make a recommendation is a big question. For example, KRAKEN would trigger each time someone made a flag because we hypothesized that a flag was the moment that in which you would change it up in your investigation, and so needed maybe a way to do so. And finally, more long-term, we want to improve and replay the exercise CERBERE. Fortunately, my colleagues are doing it, and they will be doing it at a much larger scale in a few months. And we also would like to hybridize KRAKEN and MIMIR. That is the most ambitious thing we have. It's, the idea is that both recommended systems have very, very different data inputs. And they yield very different recommendations. The recommendations of KRAKEN are very specific. They recommend actual fields to explore, but they do not understand users, while MIMIR recommends actions which are a little more abstract, but understand users better. So if we can hybridize them to understand users and actually make more concrete recommendations, we could, I believe, yield very good results. And yeah, that's pretty much it. Finally, this was a CIFRE Defense PhD thesis. It lasted 1,172 days, which may seem like a long time, but it went in a flash. I can't believe we are already there. And this yielded 3 publications, which led me to very interesting destinations. The first one was at home, because, you know, COVID. And then Sorrente in Italy, and New Delhi in India, no later than this January. And, of course, a 153 pages long manuscript, which I think everyone who read it. Thank you all, and I will be glad to answer any question you have.
Thank you very much. Time is perfect. So first, I have an apology to do because I have some tunnel vision and I forgot someone in the jury. So the last member of the jury is Simon Bosch, which is from Malisen. He's an invited and he's on the side of the supervisors. Okay, and so now it will be time for the questions, and I first give the mic to Günther Pernul from University of Regensburg.
Yeah, thank you very much, Romain, for this nice presentation. I would like to start with a very general question. So log analysis and incident response actually, I think, is a process. So it consists of several steps, several phases. And I would like to know, in order to fit your work well, to which phases you think you have contributed with your research? So I think you have something on slide 5. There is something like a process model or something like this.
Yeah, this.
Because your research is very broad. So I would like to focus it. So on which phases do you think you have contributed most?
So the part of incident response, which is effectively, you are right, a workflow, we are focusing on is the green highlighted one. It's incident resolving. And we are more focused on the action proposed step. Because we have investigations that are ongoing during our research. So the data analysis is ongoing and the resolution research is ongoing. What we want to do is help analysts go faster and more efficiently. So we propose action to them in order for them to complete their investigation much faster. Does that answer your question?
Yeah, not really, because I think if you start an investigation process, you first have to gain knowledge about which data is available. So what log resources are there, and how these log resources can be included in the analysis. And if you look at the log data, they might be of different granularity. For example, they might be of there might be a lot of heterogeneity issues and things like this. You need to combine them, you need to integrate them, and later on you start with the analysis. And I think you have not contributed to the further parts of this process.
Yes.
So you did not work on data shuffling algorithms and algorithms, how to integrate the data, but your focus was more on tools that assist the human analyst.
Yes,
isn't it?
Exactly. That's it. The ingestion part of the data and the handling of the logs and the correlating and normalizing them in order for them to be able to be analyzed is handled by the MIMIR platform beforehand, and we intervene then during the analysis when the data is already available.
Mm-hmm. 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 Okay, thank you. Shall I continue with my questions, or do we switch between the examiners?
I think you can continue.
Yeah.
Okay, then let me continue. I have a further question, not regarding the process, but regarding the threat landscape.
Yes.
So what I did not hear, and I was also not able to read in your thesis, so you are not focusing on a certain type of threat. So your work seems to be as general that it may be applied to any type of threat, or
yes,
or
exactly. Right after there, for the KRAKEN recommended system, the first one, we use the MITRE-ATT&CK database to do so, which reunites behavior of attackers seen in real life for any type of threat, and so we are able to recognize any kind of threat that appears in the investigation. For example.
Mm-hmm. Mm-hmm.
So yes.
So this is really very, very general. So, for example, would it work for a ARP spoofing attack, similar to a ransomware virus attack? to SQL injection attack. So there is no limitation.
There is one limitation. The only thing that needs to be there for us to be able to detect, not detect, but work with the attack, is that it is visible in logs. If there are traces of the attacks that can be recorded in logs, then we can find it. If the attack is too silent, with quotes, then it will be difficult to understand the situation at hand, and then the recommender system might miss it.
Because the log, or the basic idea actually is you make a similarity search and you try to find behavior that is already known in your knowledge base, and you measure somehow the similarity of a pattern during analysis, which is similar to the pattern in the knowledge base, isn't it?
Yes, but not quite the same, because the main difference is that in the knowledge base we use actual cybersecurity knowledge to make our patterns, to try to understand and recognize the cybersecurity situation, while here our patterns are solely based on the actions a user make during an investigation. So it's really the difference between focusing on the data and the user, which makes the big difference between those two.
So the knowledge base is actually quite essential to the first type of recommendation system you have developed, which is that you look at previous decisions of the analyst and try to capture what he has done in similar cases of analysis in the past, and suggest from this a certain path to follow. So, do you think the knowledge base could benefit if you would have looked more into models for knowledge representations, for example, ontologies or semantic web models and things like this?
Yes, probably. It's a very interesting question. We tried to use an ontology to build our knowledge base, because the knowledge from the MIMIR attack is closely linked to the elastic common schema, which is a common way of representing cybersecurity data.
You said what? Elasticsearch. You said Elasticsearch schema.
Yes.
Okay.
So we did use a specific ontology to represent the knowledge base, but maybe there are other models that would have benefited us more. We've considered at first using a graph representation, but in the end didn't go with it.
Okay. Another question is about data quality. So if the data you were analyzing is of, I would say, bad quality or incomplete, because logs, it used to be, so the quality of log data is not always perfect.
Yes.
So if you base your decisions on bad quality, then probably the output is also bad. Do you have any, or are you thinking about any measures that are somehow the minimum level of quality that can be used for your recommendations?
Yes, so this problem applies more to the second recommender system, because the first one is really based on knowledge, and the actual quality of the data being analyzed doesn't come into hand. But for the second one, you're right, it's very important to have good logs to analyze, otherwise the investigation traces would be wrong and the recommendations would be, might be very bad. To try and parry this problem, we did first, we used different data sets to try and to build the model. One of network logs, one of system logs, in order to try to get to be really diverse. And the second thing is that we worked on the data before using it to check if it was if the quality met base level we could use. And in both cases, for the first two data sets we've used, we believe it met the requirements. The one thing we might be a little worried about in other data sets, which we have not used to build the recommender system, but to evaluate it, is that they were created and gathered during capture the flag events. So it's slightly less realistic than actual investigations. So that may be including a bias in the results. But if it does, it's a small one. But yeah, that's all the measures we've implemented to try to ensure a good quality data.
Mm-hmm. Mm-hmm. I still have a couple of questions, but I think I would like to pass over to Marseille, because otherwise all the good questions are gone and no questions are left over for him. Is it okay for you if I pass to Marseille?
As you wish, you can have a bit more time. I mean, I don't okay, maybe we can make another round if not, but it is not the plan. So usually, if it's finished, it will be finished. So if you have one last pressing question, you can do it.
Okay. So I should continue?
Well, if you have maybe less, one or two questions, yes, you can continue.
Okay. So if I understood right, so your recommendation system goes into two directions. The first is it is based on previous decisions of the security analyst, and the second recommendation is based on the domain knowledge that is gathered from different sources. And my question now is regarding the latter one, so the recommendations that are based on the domain knowledge.
Yes.
My question is, does this mean that the system can never be as good as, so there is no learning component in the system. So it solely depends on the knowledge that is available. So there is nothing like inference of or rules, for example, that new knowledge is determined by logical inference, for example. So you only limit the level of recommendations, or the recommendations are only based on previous knowledge. There is no, for example, now we have a hype of artificial intelligence systems and ChatGPT and others, but your system somehow is meant to be very static. So what you give as input to the system will be the basis for your recommendation, but there is no learning component.
Actually, now there is. In the first version of KRAKEN, there was not, indeed. It was solely based on the quantity and the quality of the knowledge that was inside the knowledge base. But in the second version of the recommender system, we've included a feedback loop when recommendations were followed. So our idea was to say that if a user finds a recommendation interesting, he will follow it. So in case a recommendation is followed, we will influence one parameter that is used to make decisions when creating recommendations. So If a recommendation is good and is made often, an attribute we call frequency is influenced every time this recommendation is followed, and this frequency attribute is then used and has a weight in the decision for the scoring here of for the scoring part of the recommended system. So actually now there is feedback. It's not quite artificial intelligence, but it is a feedback loop. So we could say now that the recommended system is learning. We wished for it to be based mostly on actual knowledge, to be influenced not too much by user actions, but we believe you are right in saying that too static recommended systems would get bad fast.
And how do you cope with, for example, bias or something like this? So there is, or for example, if an intruder also gets the chance to manipulate the knowledge base. So he could produce rules, for example, insert these rules into the knowledge base so that the certain type of attack he will perform cannot be detected by the knowledge base or by the patterns that are in the knowledge base because the level of integrity of the knowledge base is very low.
Yes, unfortunately, we have not worked on poisoning attacks on our own tools. So I don't know. I believe it would be possible to modify the knowledge base in order to make some attacks more stealthy than others. For now, I have no way around it.
Do you consider this a risk? For example, you were also mentioning that you want to use this for integrating it into a commercial system.
Yes, it is a risk. I have to complete the answer by saying that all the resources used to make recommendations are behind all the security that is in place with the platform in which it is integrated. So it should not be that easy to get into. So it should be fine. But yeah, there's probably a little risk because risk zero does not exist in cybersecurity.
Mm. I found the way of that you have done your evaluation of your systems. I found them very sharp. So using a cyber range and collect the data from this exercise and use it for evaluation. Could you give some more information about this cyber range? So these were students, and what type of data you were collecting through this cyber range?
So this was an exercise we've put in place to gather different projects of fellow PhD students in the team, and the different important parts we have are generating a variable architecture that is attackable, with a scenario that has differences in procedures, in techniques, etc. And once we have been able to deploy these instances, we monitored them using suricata and auditing packages from the machines that were deployed. For example, auditday for the Linux machines, and all the traces are generated like so. I don't know if the monitoring changes a lot and the gathering of data changes a lot in the second iteration for now, but we aim to do so because we wanted to get back a more normalized and more formalized logs in order for them to be, as you've already mentioned, more easier to use in investigation later. But there is a whole paper we've just published in December that is about this. It's called CERBERE, and all details are in there.
Yeah, I think this is really a very sharp idea, because usually when one looks into security research, the evaluation is always a problem, because close to real world data is not available. So usually the evaluation is done by artificial data, and there might be a bias in this artificial data. So I think this is quite a sharp idea, having something like a cyber exercise and collecting data from this event and use it for evaluation of the research.
Thank you.
But I still have a question. Because this data could also be of value for other researchers. So
yes.
You are not considering or following the approach of open data and making this data available to others, or are you planning of doing,
yes,
for example, uploading it to a GitHub repository or something like that?
Actually, we already have. It is available already online. The whole label data set is all the different attack traces labeled are available on the repository. It's fully
okay. Okay, great. So this information is not in your thesis, so probably it's in the paper you have mentioned.
Yes, exactly. I can send all the details to you afterwards if you want.
Yes, please. Yes.
Of course.
Okay, I think these were my questions.
Okay, thank you very much. And
thank you very much.
Okay, so now we will have the question of Maciej Korzinski from NCMAC.
Well, thank you so much. First of all, I would like to say a couple of words about the thesis. I would like to congratulate the candidate. So there is a real empirical problem out there to solve. You mentioned during the presentation, also in the manuscript, that there are logs at the system level, at the network level, some traces left by the attackers. The data is very heterogeneous, multidimensional, very often incomplete, and clearly the idea of making better use of expert knowledge and combining this in the recommender systems sounds like a good idea. So my first question, also thank you for a very clear presentation and a manuscript. It was quite easy to follow. And my first question is about how generalizable the method is. But the question is not as broad as it sounds, because I would like to give you the stage a little bit from completely different problem, but still related to incident response remediation. And if you could explain if KRAKEN could be actually used to help the analysts in this particular case that I'm going to discuss. And then you could make one step back and discuss actually how generalizable the KRAKEN could be. Because you also mentioned that it can be used in any type of threat, so maybe we could discuss this particular case and then make general conclusions. Let's say we do have an analyst at the domain name registrar, and very often to domain name registrars there will be emails sent, for example, from the victims containing URLs with phishing websites. Now, the analyst needs to make a decision about the mitigation action, remediation action. Now, what the attacker can do? The attacker can either, for example, register domain name for malicious purpose, deploy the phishing kit, deploy the website, and start collecting, for example, credit cards or logins passwords. Or the attacker could actually compromise legitimate domain name. So the domain name is completely benign. There is a legitimate website on the index page, but the attacker exploited, for example, vulnerable content management system, let's say WordPress, and using the path, using the very particular URL, it deployed a malicious website. Now, the analyst needs to make a decision. Is the domain name maliciously registered? and it could be taken down at the DNS level, or it is actually benign and the action, the remediation action, should be taken at the hosting level by, for example, the owner, legitimate owner of the domain name and the website. Now, we clearly do not have logs here, so here the problem is slightly different, but still we have some characteristics that potentially analysts could explore. Let's say the attacker very often registers domain name and use it immediately after registration. So the age of the domain name will be very low, let's say 1, 2 days, 1 month. For compromised websites, the domain names are very often quite old, 1 year, 2 years, 3 years. So that could be one characteristic to replace the logs and the characteristics that would go to, for example, KRAKEN system.
Yes.
The attackers from time to time might use free TLS certificates like Let's Encrypt, while the benign users of compromised websites might pay for certificates. So that is another example of a field to explore. Now, my question is, would KRAKEN be, for example, KRAKEN, be adjusted to this very particular problem? How? And then more general question is like, how generalizable the KRAKEN, for example, or MIMIR could be to solve very different problems like the one that I have explained?
That's a very interesting question. KRAKEN uses a very abstract basis as knowledge base as its input data. So this is pretty easy to adapt to any situation. The problematic part arrives when we use the elastic common schema. That's because it's really mapped to logs, representation of cybersecurity logs with this way of this ontology. So if there was a way to, in any form or manner, to extract some data from, for example, these websites that are deemed malicious or not, if we could indeed get a flow of data from there, whether it's like time alive or the usage, the hours at which it is interacted with, things like that. So things we would usually consider metadata to actual logs. I believe we could probably map those to actual information that could be represented using the elastic common schema. And so we could use KRAKEN in this situation, I think, with, of course, a little adaptation work, but that could work. More generally, as long as you are able to represent the data on which you wish to make a decision using the elastic common schema, it would be easy to use KRAKEN in the situation. On the other hand, for MIMIR, all the user intentions are modeled on investigations that are conducted within the platform, and I have not had time to test it outside of it, which means it is probably the usage of the platforms that defines the most how intentions interact between them and how they follow each other during the process of investigation. So I'm not sure MIMIR could be used in other cases scenario right now. It would take us, it would ask of us to remodel completely intentions. For example, we could use techniques from UEBA, User and Entity Behavior Analytics, to remodel them. But when you're reading the literature about that, we've found that it's very general and has difficulty adapting to very specific cases in investigations. So that's why we have something that is very specific to the platform. So basically, KRAKEN could be adapted to any situation, I think. MIMIR, not so much.
Yeah, I intuitively agree. I think in the context of this particular case, KRAKEN could be relatively easily adapted, while MIMIR would probably need a lot more training, even surveying in advance people, as you did for MIMIR system in your particular context to define states, and then perhaps some form of hybrid method. So the same direction as your work is going. So thank you for this response. I would like to follow maybe another question first. Regarding evaluation, it's super hard. It's super hard in your thesis, and actually during the thesis you mentioned in the manuscript that the third part is kind of detached from the rest, which I respectfully disagree. I think it's an integral part of the PhD, and kind of without the last part of the thesis, it would be very hard to draw any conclusions about how the systems actually work, and if they can be correctly also trained. So I would like to discuss a little bit the evaluation of KRAKEN and qualitative one. There were 7 people, if I remember correctly, that were investigating the system. Now the question here is it enough?
Yes, that's a very good question.
To draw some meaningful conclusions. What can we learn from this? And in particular, there was a user 7 in the previous slide.
Yes.
That actually responded, which was I think it's slide number 49. That's 49 or sorry, 51.
Yeah,
51.
51. Yeah, yes, this one. So
exactly. And there is user 7 who found it not useful, not efficient, not relevant, not clear, and still would like to use it in the future.
Yeah.
What can we learn from this, all this evaluation, and is it representative, or it just gives some anecdotal evidence and serves more as a feedback to improve the system?
So there's two ways of answering the question. The first one is 7 is in itself not enough participants to get any statistically significant result. I agree with this. But the 7 participants we had were 7 actual experts. Among them, many of those had actual real experience working as analysts, which gives us sufficient grounds to ask them questions about the system. This is why we chose to have a user study rather than more quantitative results, because it would yield things that are much more interesting and much more reliable. The second part of your question is, what about participant 7? Well, participant 7 was the one that did not have any experience as an analyst. He was a cybersecurity expert, and he was now beginning to investigate things, and found himself in the position of a novice analyst. And so, since during the experiment he did not know the platform, the Malisen platform in which the recommendations were integrated beforehand, he spent the entire experiment trying to familiarize himself with methods of investigation using the platform. So he was really not able to use the platform, the recommender system, to the best of its ability, which is why he was not able to pronounce himself about the usefulness, the relevance of recommendation, etc. However, he did say that once he would get a little more skill in investigations, he would be able to, he would like to reuse it again to try and find out if it did work a lot. So yeah.
Thank you so much. I think that this type of studies, also interviewing people, if to learn about their experiences. Yes. When we take a look at the top tier papers currently, at Usenix, for example, security and so on and so on, there are more and more papers like this. So I agree that both qualitative, quantitative analysis are not sure if equally, but very, very important, and definitely, at least from here, you tried, and this is something extremely important to try to qualify the system. So and still we can, even if the sample is smaller, 7 users only, still I think also from the manuscript it's clear that it led to some improvements on the system.
Yes.
So my next question is related to KRAKEN once more. And you, in the manuscript, you write that you avoid the cold start problem.
Yes.
Do we really completely mitigate the cold start problem? And the second kind of part of the question is that one of the input data sets was MIMIR attack, was from MIMIR attack projects. So I'm kind of following on Günther's question. And you write there that the knowledge described, I'm talking about MIMIR attack, you write that the knowledge described covers every area of cybersecurity and every step at the possible attack. So my question is like, isn't it a little bit overstatement? That's the first part of the question, because like, what about, I will join a couple of examples to what Günther previously said. What about the DDoS slow lorries? What about DNS cache poisoning attacks? What about zero-day attacks? And the second part of the question is like, do we really completely mitigate a very, very hard problem to solve, which is cold start in this type of systems?
So for the first part of the question, yes, it might be a little overstating. It is, although what MIMIR attack claims to be able to is that in their matrix they describe any possible step of an attack, which are tactics, and then those contain a number of techniques that describe every way we have already seen attackers attack in the past. And those described are already in the knowledge base at the start of the use of the command system, which means we avoid completely the cold starts for everything that is related to known attacks and to new ways of exploiting new attacks, which means some 0 days of, for example, if you find, I don't know, a new way of doing an SQL injection, anything, or even something that simple, since we are able to categorize it using MIMIR attack, we are able to recognize the cybersecurity situation and know which type of data, which fields of logs we should explore to find out if this is the attacks we are looking at. That's the difference between KRAKEN and intrusion detection systems, for example. It's that we are not trying to detect an attack, in which case 0 days, for example, we would not be able to detect them, but we are more trying to understand that there is a security situation at hand. And then we just nudge the analyst in the right direction, in the right things to explore. And so, yes, we are able to avoid the cold start completely in this case. Which is this, it is the main characteristic of knowledge-based recommender systems, which is why we chose to use that.
It's a big claim, but still, I take your word for it also. So I have another question related to KRAKEN. So you describe in section, I think, 3.2.4 decision making in KRAKEN, and you use MADM uses orders to compute a weight for each attribute, giving the ability to score techniques. Then certain fields categorized as irrelevant are omitted. One of the components is also a simple similarity scoring. It all sounds like a machine learning problem could solve those issues. I I read manuscript carefully, and there are some hints why you haven't used machine learning, but still I would like to discuss it a little bit more, because I think that machine learning here, I would say, let's say a supervised machine learning, right? It's a knowledge-based. We have some ground truth. We could achieve all those requirements, and we could map all those steps in decision-making to some form of machine learning. So could you please, not mentioning that to avoid completely a cold start, perhaps cold start meaning knowledge-based, maybe some even unsupervised learning could be, and some form of clustering methods could be used. So maybe we could start here.
Honestly, you're probably right. We could use some machine learning models, and we could, with them, yield some very interesting results. But there are two main things why we haven't used them. The first one is why use a machine learning that gives up some transparency, some explainability of recommendations, and we don't know we don't always know the full process of decision making. When decision making that we can actually follow step by step and understand completely would work pretty well. It's a very important thing in cybersecurity to know why things are recommended. So we decided to make the trade-off, maybe, to understand perfectly why recommendations were made to us, and maybe don't have always the best recommendation. And the second thing is that we've looked into using supervised learning at first to make this kind of recommendation for KRAKEN, for the knowledge base. And regression models were usable, but once again, they would focus more on detecting if the attack was in the logs, rather than trying to understand that there is a security situation to explore there, and would occasionally blindside a user in saying, I've detected an attack, and just say, leading him in that direction, while maybe the attack is more complex, or the expertise of the user could have allowed him to go faster, or to understand more things about the bigger picture of the attack and the attack campaign, etc. So we decided against using machine learning. Yeah, for those reasons, mainly.
So I agree with the second argument. However, with the first argument regarding explainability, I do not fully agree, because then, for example, you could indeed use logistic regression. You could. The beauty is that you then have coefficients and the weight, as you also have in MADM weights, why certain event might be classified this way, and it might give you the lead, actually the weights of different fields to create the path to investigate, or for example simply a decision tree. They're also very, very explainable for analysts, but at some point, I also agree that we need to make a decision and then actually follow with certain approach. From the time perspective, at the beginning of the thesis, I believe you had some form of cold start. Now you are much more knowledgeable. A small parable also to your systems. Now, from the time perspective, would you, and here I will once more follow the Günther set the stage a little bit for LLM models. Why would you use LLM models, knowing how powerful they are these days? Would they be adaptable to solving your problems or not, and why?
I haven't studied LLMs a lot. I believe maybe they could be used to to try and describe situations at hand to help analysts understand better what's on the screen. The exploring part is much more complicated, and I don't think I have the knowledge to say if LLMs could handle that. Instinctively, I say probably they could do some of the work, yes. But I think the great strength of these things is in describing situations that are just hidden in data. So it would, at a given state of the investigation, an LLM could be able to describe exactly what is going on the screen, but maybe I'm not sure it would perform very well in terms of giving advice on where to explore next. Yeah, that's my instinct in any case.
Well, could you explain a little bit the part that LLM might be good in describing what's on the screen?
Well, given a full input of data, LLMs are very good at reorganizing the data in a very understandable manner. Is what I gather from what I may have what I've read. And so I believe that in one state of the investigation, with data in front of your eyes, if you do not understand what is going on, giving this to an LLM would help in describing exactly what is going on in a more understandable way. Where LLMs fault a little bit, I think, is in trying to infer new knowledge from a situation. And that's what we are trying to do with exploration recommendations. So maybe it would perform a little less well. But once again, I'm not an expert at all in LLMs, and I don't know much about how it is, so it's really just an instinct.
I think that the second part, I fully agree that without some form of fine-tuning of the model, yeah. And passing the knowledge to the LLM model might perform not that well. On the other hand, for perhaps active learning afterwards, it could be interesting. Yes. Okay, so my last question. So I really enjoyed or liked the empirical nature of the problem. And I would like to ask how far your systems are, what needs to be done, I would say, scientifically, empirically, so that it's really fully operational and helpful in the context of investigations. How far you are in the systems are.
Well, that's a nice question for me, because they are already fully operational. They are integrated to the investigation platform Malisen develops, and they are being used by the company and the clients right now when they need it. At least KRAKEN is very well integrated into the workflow of investigation now. MIMIR still needs a little bit of fine-tuning, for example, on the frequency and the trigger of recommendations. But overall, we are pretty much set, and it's already ongoing, which is pretty great.
Yeah, that's indeed quite rewarding. So thank you so much, and I will leave the stage to the next person.
Thank you very much. So the next person, so we now go to the examiners, and we have the last person in Visio, which is Vincent Nicomet from INSA Toulouse.
Okay, can you hear me? It's okay?
Yep.
Okay. Thank you for your manuscript. Thank you for the presentation. I try to be short because I think you must be exhausted now. I have some detailed question and some more general question, but I'm going to start a question about KRAKEN. Okay, you use the MITRE attack information, and you use technique And I thought I was thinking that when I am an analyst, I investigated some data, and this is very specific data. I'm trying to investigate port source and IP address, etc. And this make me think about the procedures and not the techniques of the MITRE attacks. So I was wondering why didn't you use directly the procedure? Because in the procedure you have all the technical data that can explain how an attack can be made, etc. And perhaps the data that you are looking for when you are an analyst correspond to the data that are described in the procedures. So I had this question.
You're right. Our first instinct was to actually use procedures as well. So yeah. But we've rapidly found out that there are two main things that allowed us to use techniques. First, techniques have a specific attribute that is data sources, where the attack is often recorded from. And these data sources allowed us to make a direct link to the elastic common schema and link those data sources, and so indirectly those techniques, directly to actual fields that were explorable in the investigation platform. So that made it
Okay, I understand, but did you perhaps you missed something by ignoring the procedure? Don't you think so?
That's possible that for specific procedures they have, for example, a much simpler way to observe them in another source of data that is not recorded in the technique level. But and so we might have missed a few things. But I think it's still better to use techniques because the number of procedures is exponentially more higher than the number of techniques, which makes it a lot simpler and less complex in terms of computing to use techniques.
Yeah, I understand. Okay. Another question. I think your last slide was very interesting because I think KRAKEN really depends on the data that you're using. You're using quite static data from the MITRE attack, and you talk in your last slide about using more dynamic, up-to-date data, I think, by using CTI.
Yes.
I think this is really something really interesting to my viewpoint. So can you say more thing about that? Can you imagine how you could inject some fresh data in KRAKEN from CTI? Do you have an idea how you could do that?
So yes, we kind of do. The idea would be to attach to techniques reports of CTI reports that correspond to them, either in terms of attackers, groups that have been identified using some techniques and how they realize them, things like that. Our main problem to try and test out this new input of data for KRAKEN is that the time component. There is a big problem with logs. It's that logs have their own time. An investigation has its own time, and the validity of CTI has its own time as well. So we have to compose between those to know when to make some CTI available during an investigation, if it even concerns the data we are investigating. And so we have not found yet a model in which we can mix all these different way of showing time. And once we find a solution, I think we can start trying to link it with the MITRE attack database.
Okay. Just a little question, because I'm not specialist at all in MITRE attack. Several times in your manuscript you talked about the attribute of the techniques. I couldn't find on the website MITRE attack the attribute. When I visit the website and when I try to see a technique, I see the procedures, I see the mitigation, but I do not see the attributes. They are precisely defined somewhere in the website. That's it.
There is. If I remember correctly, if you are on a technique, there should be some kind of, not pop-up, but some kind of square on the right side of the screen that shows some characteristics of the attack, of the technique. And in fact, when we when you download this data in order to use it, it's represented using a format that's called sticks v2, and it shows it has different types of attributes, and this is where we gather them. All the attributes are described using this format. I don't really know where they are in the website again.
Okay. Thank you. So I have a question to MIMIR now. I was wondering about you have two phases, if I clearly understood. The design phases and the running time phase. Okay, design phase and running phase.
Yes.
So during the design phase, this corresponds to investigation conducted by different analysts that you observe. Am I right?
Yes.
Okay. So I think it strongly depends on the analyst you use for the design phase.
Yes.
So did you try to perform a lot? I think it's difficult to say a lot, but several design phases to see if there is a difference. If there are differences, if you perform this phase with different analysts. The different backgrounds, the different way of acting, or you understand what I mean?
Yes.
I mean, is your design is not they are not biases because of the person you choose.
Yes, absolutely right. Unfortunately, we have not had time, nor the participants, to build new design phases right now. But so this is the experiment for the design phase with the participants and the investigations they conduct. And of course, it has to introduce a bias. But when we extract the intentions and the patterns from those investigations, we kind of reduce and minimize the problems that could arise from this small pool of participants by matching those with how expert users of the platform would do to realize said intentions. So in doing so, we don't fully address the problem, I think, but we minimize it as much as possible, probably.
Okay, thank you. Another point is MIMIR. I remember the name. Yes, MIMIR. MIMIR is very specific. It's specific to Malisen because you use a couple of actions, which are very specific to the interface, the investigation tool Malisen.
Yes.
Just a few remarks. I spent a lot of hours trying to understand what mean drop card. I was really because I didn't knew what was this action, and you didn't explain in the manuscript, so I really didn't understood we didn't understand what means drop card, and I realized today during your presentation what it is. It was funny. I really didn't
thank God for the video then.
Yeah. Okay. So it is specific because the action that you have for MIMIR are really specific to Malisen, but do you have an idea of how can it be adapted to another investigation platform with different action? Do you think it's quite easy to adapt MIMIR to another investigation platform?
No, I think it would be quite hard because at first, when we started developing MIMIR, we tried to make it as generalizable as possible. And we tried to abstract user actions as much as possible while retaining the intention that were behind the actions to make them applicable to other platforms or other ways of investigating. And the results we got in terms of matching user intentions with patterns and then recommendations were a lot worse. So we said that's why we are using a very specific model. We would need to redesign entirely how we select actions and how we define them for them to be more generalizable, I think.
Okay, I have two more questions and then in the end, I promise. I have a question about the time, the moment where the recommendation appear on the platform. You talk about that in your last slide.
Yes.
I think this is very important because it can be unproductive. I don't know the word is correct in English, but not productive. You see what I mean?
Yes.
Because if it appears too often, probably it may deconcentrate the analyst, and it could be not productive. So, do you have an idea of the better moment for the recommendation to appear on the platform when the analyst is performing his job?
So yeah, that's the whole discussion. I don't have a definite answer because honestly, I don't know when is the best time to make a recommendation. I believe we've found a good way of doing it with KRAKEN. After a flag, it seemed to be working pretty well and to not happen too often and work. For MIMIR, we first made the recommendation every time we detected a pattern, which, as you have guessed, flooded the analyst with recommendations, distracting him, which was not good, evidently. So what we are working on reducing the frequency of recommendation by trying to understand more, a little more about the context in which investigation is. So, for example, when the same intention is detected multiple times in a row, we could adapt the number of times we make recommendations, and that's a work in progress, but it's coming along.
Okay, thank you. So, another question. Perhaps I missed something because I couldn't read your manuscript as carefully as the reviewers. Perhaps I missed something, but I think for me, the main goal, interest of this recommendation system is to reduce the investigation time. Okay, and I didn't see something in your manuscript when you try to measure the investigation time with and without your recommendation system. Did you do that? And sorry if I missed something.
No, you're absolutely right. It's something that is very difficult to evaluate properly. For the first experiment with KRAKEN, we had only 7 participants, and so we were not able to make multiple groups to do a double-blind experiment to check if the investigation times were significantly improved. And the second exercise was the second evaluation for MIMIR online. I mean, was done during a blue team exercise. So the same. Similarly, we could not just not give the recommended system to some people, and so in the end, yeah, that's the dark point. I think we were not able to measure the improvement in investigation time.
Okay. Thanks a lot again.
Okay, thank you very much. And so now give the floor to Laetitia Leichnam from Pepsi.
Thank you. Well, thank you for the presentation. It was very clear. And so as a soccer manager, I appreciate the fact that you work on getting the soccer analyst way more easier. So it's a really good point that you're working on that. I think that you capture well the intention of a soccer analyst with the 7 intention.
Oh, thanks.
I think it's describe well the way analysts are working by exploring data. I have 2 questions for you. The first one is about MIMIR. I was wondering, as you said that you are integrated in MIMIR.
Yes.
And you have use customer data and you get some results, I suppose. Do you see any difference between the way it works with customer data and the way it works with the CERBERE exercise?
So we don't have a lot of customer data right now, but I have not analyzed this for now, so I don't really know if there's big differences between them. But I expect there will be, I think, because one instance is really a capture the flag game, and the other is an actual investigation, real work. So I believe there will be some changes in the way intentions follow each other. It might be influenced quite a lot by habits of analysts, and this is what we expect to find as differences, but I have not had the time to do it yet. Sorry.
I think more about the fact that in listening data you have maybe some misconfiguration, misusage on the customer. Behind true positive and false positive, so you have much more chance to get to dead end.
Yes.
So it would change the probabilities in the matrix, I think.
Yes, you're very right. That is why when I was talking about the perspectives in the future work, we would like to try to understand more the context in which the user is investigating to not rearrange, but to recompute the probabilities in the matrix. Because if we understand what step of the investigation the analyst is in, for example, if it's in the discovery phase of attacks, if it's documenting the attacks that are already found or making a report, the chaining of the intentions might be very different, and we might be able to parry the problem you're discussing using that, but that's unfortunately for the future. But I hope it would work like this.
And the next question is in fact related to the previous one. It's about the investigation patterns. I think it's level 38.
39, yes.
39. If you use another tools, more complex, there will be way more investigation patterns. Is a recommendation engine scalable to have much more patterns?
I think if you can overcome the hurdles of redesigning your patterns for a new platform and probably changing the intentions that are associated by matching them with the patterns probably a little differently. If you can do this, then it's all modeled into a Markov chain. And if you don't explode too much the number of possible intentions, it's very much scalable, I think, yes. It's just a matter of how much data you want to give out to the user for your recommendations. So, for example, if you have still 7 intentions, but you want to not only recommend the next most probable intention, then maybe a combination of the most probable things you could do and maybe different patterns of actions that could be undertaken by the user, maybe understand the actions that are available to the user at this time and influence the patterns that way. The complexity of making the recommendation becomes much higher, and then the scalability decreases, I think, for the tool. But if you stay in this state, it's very much scalable, I think.
Thank you. So, I'm sure that you will soon rest. I will ask my question, and then you will have your supervisors, which may not ask questions. Okay. Many good questions have been got. First, I have to thank you for the presentation because I know nothing in cybersecurity, and you made a very clear, very easy to follow presentation. So
thank you.
It was nice. So we have a question on patterns. So you have very small patterns.
Yes.
They are only with 2 elements. You said okay. You have this in your perspective to work on finding more complicated patterns. So my question would be, from what you have seen with your users, I have 2 problems. First, is there a lot of noise which breaks patterns, which makes them hard to find? First question. Do you think that with your knowledge of analysis, there would be some interest if you can overcome noise to analyze patterns that are longer than 2? And okay, longer than 2, but it's still a sequence. Do you think that in general people are following a sequence, or because you have your backtrack, it should be more interesting to analyze some kind of a tree or perhaps a DAG? So look at this and that, and after do that.
That's a very good question. Our first idea for patterns was to actually make a tree, to really entirely map out the investigation process. But we found out that it was very complicated to detect when you are at a dead end and need to go back up in the tree. And so we moved on to using only patterns. Then we experimented with patterns of different sizes. We went from 2 to 5 the number of action in the pattern, and with or without context. What we found out is that pattern of 2 action capture as much intention as pattern of 3, 4, or 5, because patterns of 3, 4, or 5 actions are often the same ones or combinations of patterns of 2 actions, but with actions switched up a little bit. So we stayed on patterns of 2 actions, and the other reason why we did that is because exactly of noise. We managed to suppress some of the noise by not considering actions that are not relevant in a cybersecurity standpoint, which means some interactions with the graphical interface. For example, the cards you see, we can resize them. That's an action. So that's noise for us because it doesn't really have an interest for the investigation in itself. So we suppress those, and the patterns are really concentrated parts of intentions. And it worked with patterns of 2 actions, so we just went with it. But I think if we want to make it more reliable, we should try to build a tree. It will be a lot more complex, but I think that would be the best way to go.
Okay, thank you. Okay, now go to your supervisors, and well, I will start with Simon Bosch from Malisen.
I have a question. Oh, yes, I can say a little bit. It was really a delight working with you. It still is, and I'm really happy with you. Thanks.
Good, so now it will be Frédéric Mazurczyk from DGA.
So I won't ask any questions too. Just add a few words. So it's maybe 4 years that we work together from the beginning of your internship, and I thank you to have trusted us to do this thesis. I will focus on the fact that evaluation is quite difficult in this domain because we have to do with people to prepare the experiment and so on. And focus on another point that last months of 2023 were quite intense. There were many deadlines. Yeah. And I think Douglas Adams said that he loves the sound of the deadlines when they pass by. And sometimes we don't have freedom to enjoy that. So thanks again to have respected all these deadlines and being here today.
Okay, and so last is Jean-François Lalonde from Centrale Supélec.
Yeah, so of course, I have no specific question about your work. I have some comments I want to say. So, 2 comments on your work. One is the place of your work in the literature. The literature about the recommender system is quite large, so it was good work to work on all these papers and look at them. And at the same time, there is not so much papers that are working on the cybersecurity problems. And so your work is one of the first in the field. You are the kind of the first explorer doing that. And I think that it's always fun and interesting to be one of the first to propose new things at the crossroad of two fields. Another comment about your work is the fact that your work is a joint work with the industry. The tool recommender system you have designed are integrated in a real software, it is used these days by experts, and it's not so often the case that the work of a PhD student becomes a real used work. So I want to highlight that because I think it's a good result. You have managed to perform this work at the crossroad of academic work and industrial work. I have final remarks about you and your work. I want to thank you about the autonomy you have to perform this work. All the ideas you have pushed here are from you, and at the same time, each time you push your ideas, you listen carefully about us, about what we think, about the remarks, and we can discuss things. So it's important to have this quality of discussing the ideas. You are an efficient guy, I would say, because you work very fast. Even sometimes you work too fast because we give you something to do and it's done magically, and you come back to the meeting and it's already done. So we have to work again because you work too fast. So thank you very much for these 3 years, and I want to congratulate you about your exam.
Thank you.
Right, so I have to ask you a question. Is there someone with a PhD in the room that really wants to ask a question? The answer is no. So you're finished for now.
Ok, donc, je parle en français. Romain Brisse a effectué une présentation très claire et pédagogique de ses travaux, intitulée « Recommandations d'exploration pour l'investigation d'incidents de sécurité ». Le jury a apprécié sa capacité à mettre ses travaux, qui provenaient pourtant de domaines techniques, à la portée de scientifiques non experts en cybersécurité. Il a aussi apprécié l'excellente motivation des contributions et les choix effectués pour éviter de surcharger le discours. Les travaux de Romain Brisse se situent dans le domaine de la cybersécurité, mais en utilisant des systèmes de recommandation. L'exposé a montré la maîtrise de Romain Brisse dans ces deux domaines et sa capacité à allier ses approches de manière pertinente. Les travaux, réalisés dans le cadre d'une thèse CIF avec Malizen, sont déjà intégrés aux outils de l'entreprise et en production. Outre ses contributions scientifiques, une contribution importante de Romain à son domaine a également été la réalisation d'un nouveau jeu de données original pour l'analyse d'attaque dans un scénario réaliste. Romain Brisse a répondu avec aisance et maturité aux nombreuses questions du jury, démontrant non seulement son expertise, mais aussi le très grand recul qu'il a pris sur ses travaux. Pour toutes ces raisons, le jury unanime décerne le diplôme de doctorat spécialité informatique de Centrale Supélec à Romain Brisse. Félicitations. Merci.
Vous prêtez serment maintenant.
Je peux prêter serment si tu veux.
Je vais prêter serment. En présence de mes pairs, parvenus à l'issue de mon doctorat en informatique et ayant ainsi pratiqué dans ma quête du savoir l'exercice d'une recherche scientifique exigeante en cultivant la rigueur intellectuelle, la réflexivité éthique et dans le respect des principes de l'intégrité scientifique, je m'engage pour ce qui dépendra de moi dans la suite de ma carrière professionnelle, quel qu'en soit le secteur ou le domaine d'activité, à maintenir une conduite intègre dans mon rapport au savoir, mes méthodes et mes résultats.
Oh.
C'est à moi de parler maintenant. Très bien. Je vais le faire en français, si vous me le permettez. Je suis très heureux d'en arriver là. Comme j'ai dit à la fin de la soutenance, c'est quelque chose qui est arrivé en 3 ans et quelques mois, mais finalement très 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 vite. Je dois avouer, j'ai du mal à réaliser que ça y est. Ces 3 ans que j'ai énormément appréciés, non seulement de par le travail et l'environnement dans lequel j'étais, mais aussi les personnes qui m'ont entouré, que ce soit mes co-doctorants, mes collègues, que ce soit ici à Centrale Supélec ou à Malizen, et mon encadrement. Et ouais, je vous remercie tous beaucoup de m'avoir aidé de quelque façon que ce soit. Et j'ai hâte de continuer à travailler peut-être avec vous un jour. Je vais m'arrêter là. Très bien. Eh bien, si tout est terminé, pour ceux qui sont en présentiel, et je vais repasser en anglais peut-être. For everyone that is in the room here, there is some food we can eat together. I'm very sorry for the people that are far away. I wish I could send you some, but this is going to be complicated logistically. So I thank you for coming a lot. Thank you for reviewing my PhD. Thank you for reading it and listening to me. It's a great pleasure to have you. And for all those, I'm available to further question, even let's be mad, but with some food and a drink. Thank you so much.